exponential function. Okay, so we're going to go back over transformations of functions, and then we're going to look extensively at exponential functions. So let's remind ourselves about transformations. So when we take a function, shifting it left, right, up, down, stretching it, compressing it, reflecting it, those are transformations on a function. So remember, when a transformation affects the x, it does it in the opposite manner. So if we had this function, f of x equals 9 to the x, if we did 9 to the x minus 7, we have to think, what's the opposite? Minus 7 makes me think left 7. What's the opposite of that? Right 7. So if we have something added or subtracted to the x, that causes a horizontal shift in an opposite way. So this will move it right 7 units. All right. Now, when the transformation affects the y, it moves it in the same manner. So, if we have something added or subtracted to the end of the function, that's going to shift the entire function up or down. This minus 8, since it does it in the same manner, is going to shift the entire thing down 8 units. The next one, when a function is multiplied by a number greater than 1, that causes a vertical stretch. So this one has a 6 out in front, which causes a vertical stretch by a factor of 6 to the original function. Now, with exponentials, they either increase or decrease rapidly, depending on our base to start with. So sometimes it's hard to see a vertical stretch or a vertical compression with an exponential function. The compressions are easier to see, but the vertical stretches are harder. Because we take a function that looks like by hand, curved like this, and then we pull it, and it makes it curve a little bit faster. Okay? Now the vertical compression would take this curve and squash it. So you can kind of see when the curve is less steep that it's had a vertical compression, versus a vertical stretch is a little harder to identify. So if this number out in front is a fraction between 0 and 1, that causes a vertical compression. Now, we're not actually going to move numbers inside here and cause horizontal stretches or compressions. We're not going there, so don't worry about that. Now, we also can have reflections. If the reflection, as in this case, is up with the x, if the negative is up with the x, it switches all the x's to the opposite, which causes a reflection over the y-axis. And then we have one more that it appears I've left off. If we have a negative out in front, like that, it causes a reflection over the x-axis. And these cause a reflection over the y-axis. So add that in, guys, since I left that off. Okay, now these two right here, let's go back to that for a second. We know that when we raise something to a negative exponent, that negative exponent can be the same as 1 over that. So these two transformations actually mean the exact same thing. So if we started with this one, both of these cause that reflection over the y-axis, whether it's written with the negative up with the exponent, or if we choose to do the reciprocal of that base. Both of those mean the same thing. All right, so let's look at these examples, and then after we do these, you guys will have a chance to get started on your homework assignment. You should have about 10 minutes, maybe 15 minutes of class time to get started. All right, so we're going to start off with this original function. On this first graph, I want to graph both of them, just because it's been a long time. So here we have f of x equals 3 to the x. And guys, what we did way back when was we picked some x values. Now these are the 3 that I like to always use. Your teacher may have had to use 5. I'm good with 3. So if you'll do 3 x values. So what we would think in our head, and what we're actually going to write in a table, are the moves for, this would be called the parent graph, because this is just a base raised to an exponent, and there is absolutely no transformations to this. It's not shifted left or right, it's not shifted up and down, there's no reflections, there's no stretches or compressions, it is just your basic exponential function with nothing extra. So that's what we call a parent graph. So if we do 3 to the negative first, because that's what our y is. Our y is 3 to the x. So if we do 3 to the negative first, that's a third. It flips it. If we do 3 to the 0, any number to the 0 power, except 0 to the 0, it's 1. And then we do 3 to the first power. And 3 to the first is 3. So on this case, we're going to graph this first function. And it looks like this. Now, let's talk about this again. Is there any way to raise a positive base to a power and get out a negative number? No. So this function will never come down here because it can never be negative. Is there any way to raise a positive base to a power and get out 0?
Yeah.
No. It gets as close to 0 as it can possibly get, but it never gets there. So what happens with an exponential function is our graph is going to have an asymptote. An asymptote is a line that the graph approaches, but it never touches. It gets closer and closer and closer to it. Now, this is one of these really weird theoretical concepts that it's hard to grasp. It just doesn't make sense that we would never get there. But we get there, we get closer and closer and closer and closer and closer forever to it. Now, every year when I talk about this, I have a student that questions. And I love that. I love it when you guys question me. And they worked on their calculator for like 22 minutes. And they're like, aha! I got there. Well, what happened was the calculator eventually rounded it to 0. And it will. If you work on your calculator, if you type this in and you go as far as you can towards negative infinity for x, eventually your calculator is going to tell you that you get a y value of 0. But what it really did is it rounded it to 0. It doesn't actually ever hit or touch 0. So here's our asymptote. Here's our graph. That graph is getting as close as it possibly can without ever touching that line. Okay, so this is what you worked on a good bit in 9th grade. And then what we did was we said, okay, let's take this idea and let's shift it. What would this function, how would it change this one? What's different?
Go to the right,
Left 4. So it's going to be a shift left 4 units. Nothing else about that function changes. So when we graph these, this part stays the same. We keep thinking about that part. But we have to start graphing it in a different spot. So what we do is we go, all right, because of this transformation, I'm not going to start graphing here at the origin. I'm going to start graphing 4 units to the left. 1, 2, 3, 4. I'm going to start graphing, and I always put a little crosshair right there. This is my new starting point for this function. Nothing else changes except where I started. So all these moves stay the same, but they start from right here. So I go left 1 up a third, 0, 1, right 1 up 3. So it takes that whole function and just shifts it right over here. And we're done. Now, we're going to do the descriptions. Whoa, apparently I'm just going to scribble everywhere. We're going to do the descriptions from that second graph, the shifted one. Now, there is absolutely no restriction on the x values that I can use. When I describe all the possible x values for this function, there's no restriction. It's all of them. So it's from negative infinity to positive infinity, or like if you're taking a standardized test, all real numbers. I saw several of you taking the SAT, not the SAT, the ACT Saturday morning, waiting in line. How was it?
The math was easy, but the science was.
The science was hard.
Science is honestly like literally just reading.
Yeah, it was like it was so like I was getting to the point like I was like I want to be done with this honestly.
Okay. Okay. Oh, you took the essay part.
Yeah, I did.
Okay, you did too.
Topics are always pretty stupid.
Yeah.
Okay. Did you? All right. Okay. So, second period told me there weren't any transformations on this version of the ACT. Did you guys see any transformations?
No,
Okay.
and there wasn't logs.
And there were no logs on this one. Okay.
Not on my version.
There's
Okay.
no natural
No natural logs, no logs. Okay.
But there might be on the next.
It was on the last one, and so were rational functions. Okay. Okay.
But
I guess it's hit or miss. You never know.
why is there a section up in the back that we don't do at all?
The fifth section, there's a testing section that they only do during some of the test, and it depends on the date and your location. I read about it, and then I was very hopeful that my daughter wouldn't have to do that fifth section. All right. So the range is all the possible y values. Now, we talked about these y values will never get negative. It's not possible. There's no way to raise 3 to a power and it become negative. So, and we said it's going to get closer and closer and closer and closer to 0, but never actually equal 0. So, when we go to do the range, it gets as close as it can, but never equals 0. So we have to use a parenthesis right here. To infinity. Now, if the next version of the SAT or ACT that you take does have a range like this, they might write the answer like this. The y values are greater than 0. These two things mean the same thing. This is as an inequality. This is as interval notation. These two things mean the same thing.
Well, it never touches 0 though.
It doesn't. That's why we can't put equal to.
Or bracket.
And that's why we can't use the bracket. Because it never can be 0.
But if
Good
it's not
point.
a 0, then you bracket it. Like,
If it could equal 0, then we put a bracket. Yep. All right, so this next one, let's take a look at this. Do you see we're dealing with the same beginning function? The parent graph stayed the same as the first one. So I'm not going to regraph that because I know what that parent graph looks like. So I'm going to deal with the second one now. The second one says take that parent graph and the only change is this, up 1. Well, when we take that whole function and shift it up 1, what I want you to think about it doing is shifting that asymptote. So that asymptote no longer lives at y equals 0. It's up here at y equals 1. So our asymptote is what gets shifted up and down. So please go ahead and shift your asymptote. Okay, now that's the only transformation that's made to this function. There's no left or right, there's no reflections, there's no stretch or compression. So all I did was shift the asymptote. So my starting point would be right here. Instead of at the origin, it moved up 1 unit. And then I go back to these moves. 3 to the negative 1. If I go left 1, I go up a third. Because 3 to the negative 1 is a third. 3 to the 0. If I went left or right, 0. 3 to the 0 is 1. So I go up 1. 3 to the first. If I go right 1, it's 3 to the first. 3 to the first is 3. And there's my graph. So do you see, I don't really have to do the chart. If you want to, you're certainly welcome to. But if you can shift the asymptote and your starting position and kind of do the chart in your head, you are more than welcome to. All right, so let's do domain. There's never going to be a restriction on the x's, so that domain will always be from negative infinity to positive infinity, or if you're taking a standardized test, they might call that all real numbers. Now the range, we shifted it up 1. So instead of being 0 to infinity, it is now 1 to infinity. So if you were taking a standardized test, that might look like that. All the y values are greater than 1. So when we're describing this transformation, what changes from just your basic base raised to an exponent to this whole function? It shifted up 1. Breakfast of champions.
That was my grade. I like it. That and orange juice.
At least you ate this one.
Chocolate.
Is that not a breakfast champion?
It's what I had this morning, so I'm not. Alright, so number 3 is the same function, like f of x equals 3 to the x. So our paragraph is the same again. But this time we have this 2 out in front. And that 2 out in front causes a vertical stretch. Because this number is bigger than 1, it causes a vertical stretch. There's nothing added to the end. There's nothing added or subtracted to our x. So there's no shifting left, right, up, or down. That asymptote doesn't move. The asymptote is still at y equals 0. So how does this one change?
Vertical stretch by 2.
It is. So what it does is it takes those normal moves of 3 to the negative 1 being a third, 3 to the 0 being 1, 3 to the first being 3, that we can really do in our head, and it takes and doubles them. Because of the 2, each one of these y values gets doubled. So I go left 1 up 2 thirds, right or left 0 up 2, right 1 up 6. So that 2 causes a vertical stretch, and it multiplies your y's by that number. So we go left 1 up 2 thirds, a little higher, up 2, right 1 up 6. Now, it's really cool how the graph kind of ties into what we already know about a function that's in this form. When it's in this form and there's nothing extra, y equals a times b to the x, we know that a is our initial amount. What is the y-intercept of this function? 2. Now that only works when it's in this form, y equals a times b to the x, and there's nothing extra. This multiplier ends up being your y-intercept. That's our starting point. All right, domain, still the same. Range, still the same. 0 to infinity, it's the same as the parent graph. But this time we have a vertical stretch by a factor of 2. And I'm okay if you just say by 2, even though it means by a factor of 2.
Say just stretch, or do we have to say vertical?
We should say vertical because there's actually 2 different kinds of stretches, even though we're only doing vertical right now. There's a horizontal stretch, yeah, but we're not going to mess with those with exponentials. Exponentials are hard enough to see what the changes anyway, so we're not delving into that. Now, 4 and a fourth are reciprocals. And this could be written as 4 to the negative x. I could give it to you this way or this way. So we're going to graph both of them this time since we have a new base. We're going to graph this one in pink. So f of x equals 4 to the x. There is no shifting. There's no vertical stretch of compression. There's no reflection. There's none of that. So 4 to the negative 1 is a fourth. 4 to the 0 is 1. 4 to the first is 4. That is the graph of f of x equals 4 to the x. That is a basic function. So this 1/4, which could be written as 4 to the negative x, this negative just switches our x's to the opposite. So it reflects it over the y-axis. So instead of being positive 1/4, it's negative 1/4. It just reflects it. Oh, that should not look like it's going back up. Sorry about that. So my domain for both of these is negative infinity, positive infinity. My range for both of them is from 0 to infinity. But this g of x, when I describe the transformation, this is a reflection over the y-axis. So when I negate the x, or I use a reciprocal, it's a reflection over the y. So let's talk about what it would look like if it were a reflection over the x. What would I take right here to make it a reflection over the x? I'm going to make up a new function, call it h of x. If I throw the negative out in front, you're right. The negative out in front causes that reflection over the x. So we're going to say h of x is a reflection over the x. And in this case, I cause g of x to reflect. So that would plot this point down here. That would plot this point down, 1, 2, 3, 4. Sorry, I missed it. Down here. That point would go right there. So if I reflected this blue graph, which is g of x, if I took that g of x and threw that negative out in front, a negative out in front causes a reflection over the x. It changes all of your y values to the opposite. So a negative here causes all the x values to change to the opposite. A negative out in front changes all the y values to the opposite. Do y'all remember that? Okay, cool. All right, so let's kind of use 5 as a challenge. What if we didn't graph the first one and we just tried to graph the transformation? How do we start?
Vertical stretch by 5.
Vertical stretch by 5, very good. And what does this 3 do?
Shift down there.
A vertical shift, down 3. And that's where we start. We always start by shifting the asymptote first. If it doesn't shift, we just draw it right on top of that x-axis. So our asymptote is down here at y equals negative 3. Now, my base to the exponent is 2 to the x. So in my head, or if you want to write it down, you're doing 2 to the powers. So 2 to the negative first, 1/2. 2 to the 0, 1. 2 to the first, 2. Because my base is 2, these x values cause 2 to the negative first to be 1/2, 2 to the 0 is 1, 2 to the first is 2. So those are my basic moves, but you guys already told me there's a vertical stretch by 5. So that multiplies all these moves by 5. So from this shifted starting position, I shifted it down 3. This made me shift it down 3. I'm starting right here. I go left 1, up 5/2. 5/2 is 2.5. Boom. Left 1, up 2.5. Okay, left to right 0, up 5. Left to right 0, up 5. And then right 1, up 10 is totally off the graph. And we have this very stretched out exponential function.
Subtract by 3 then.
Yeah, the -3 caused it to shift down 3. So my domain is from negative infinity to positive infinity, but my range is from -3 to infinity. That's not infinity, that's 8. Okay. Let's sneak back to this last problem. What would the range of that reflective green graph be?
Yeah, infinity to 0.
Negative infinity to 0. Awesome. Okay. So this one, when we're talking about its transformations, it was shifted down 3 units. And a vertical stretch by a factor of 2.
Yeah, I thought that was 5.
By 5. You're correct. I didn't spell stretch right a second ago. Y'all were really sweet not to tell me.
I didn't even notice.
You didn't notice? Okay. Alright, so you try number 6.